So here we've got two waves, or sorry, one wave, but two graphs of it. And in this case, instead of having an X graph and a T graph, we have two X graphs. I forgot to label that one, but two X versus Y graphs at different times. One of them, a snapshot of the wave at 6 seconds, and the other a snapshot of what the wave looks like at time 10 seconds. And we want to figure out, as usual, the various properties of the wave, including which direction it's moving, which is kind of difficult to do from two X graphs because we don't have much information about time. But what can we figure out from just the X graph?
Can we figure out the wavelength?
Yeah, and based on this graph, what does it look like the wavelength is from crest to crest or trough to trough?
6.
Yeah. Looks like, for instance, 4 is a crest and 10 is the next crest. So that's 6 meters away. So we can say the wavelength is 6 meters, assuming this is measured in meters. And the period we can't measure directly because we don't have any graph of time. Amplitude is not really shown on this graph. Let's just treat it as A or just assume it's 1. But for the other information, we can't really find a point in common on these graphs like we did for the T and X graphs, because there isn't really a point in common. For instance, the first graph shows all X values, but only what time value? What's the only value of time on this entire graph?
Time equals 6.
Yeah, for this whole first graph, time is 6 seconds. And there's no way to find time 6 seconds on the other graph because that whole graph is time equals 10 seconds. So since these two graphs are at fundamentally different times, there is no point in common. But what we can do instead is take a look at one type of point on one of the graphs and figure out where it has moved to by the other instant in time. For example, if I usually choose a point near the center of one of the graphs, let's say we're looking at maybe this crest or this trough. There's a trough at 7 meters, X equals 7 meters at time 6 seconds. What we want to do is figure out how far that trough has moved by the time we get to 10 seconds. Maybe this trough has moved to the left, or maybe it has moved a little bit to the right, or maybe it has moved a lot to the right. We don't know yet. In fact, there isn't really a way to tell just from this much information. We're going to need one more piece of information. And typically that one more piece of information is something like the speed of the wave. So let's say that is given information. Let's say this wave has a speed of 2.5 meters per second. So let's assume we know that the wave speed here is 2.5 meters per second. Maybe we know what medium it's traveling in, and we know that that medium provides a speed of 2.5 meters per second. That actually gives us a lot more information as well. It unlocks a lot more ideas, because if we know the speed and the wavelength, what else can we immediately find?
A frequency.
Yeah, we can find the frequency, or yeah, the period, same information. So if we use the idea of speed and how it's related to wavelength and period or frequency, we can say speed equals wavelength divided by period, or speed equals wavelength times frequency. Either one will get you the same information. We know the speed is 2.5 meters per second. We know the wavelength is 6. So let's go ahead and figure that out. 2.5 meters per second equals wavelength, 6 meters, times frequency. And then how would we solve for frequency?
Divided by 6 for both sides of the equation.
Yeah. Right, divide both sides by 6. So frequency is 2.5 over 6, and then meters cancel out, so we get 1 over seconds, also known as hertz. And 2.5 over 6, if we double the numerator and denominator, we get 5/12. So the frequency is 5/12 hertz, or we could say the period is 12/5 seconds, or 1.4 seconds, no, 2.4 seconds. So we can describe the frequency as 5/12 hertz. We can describe the period as 12/5 seconds or 2.4 seconds. So let's go ahead and fill that into the equation as well. Any questions on that so far, based on the given wave speed?
No.
And then to figure out the direction of travel, because we're going to need to know the direction using plus or minus before we figure out the phase shift as well. To find the direction of travel, like I said, we want to figure out this trough, for instance, we want to figure out which trough corresponds to that on the other graph. And one way to do that, we know the wave speed, that's given information. We also know these two graphs represent how much time apart from each other.
Four seconds.
Yeah, these graphs, it's a horrible color. There we go. These graphs are 4 seconds apart in time. So we know that between these graphs, 4 seconds pass. We also know the wave is traveling at 2.5 meters per second. If you know the speed and how much time has passed, what else can you figure out?
Wavelength, but we already know the.
Well, we already know wavelength and period. But think back to what speed means. Ignoring waves entirely, just the original meaning of speed. What is speed?
It's change of position over change of time.
Yeah, change of position over change of time, delta x over delta t. We know the amount of time that has passed, 4 seconds, so that's delta t. What can we now solve for?
The distance.
Right, delta x is the distance traveled during those 4 seconds. So if we solve this for delta x, we get speed times time. We know the speed, 2.5 meters per second. We know the time, 4 seconds. Multiply those together, we get 10 meters. So that means during these 4 seconds of time, the wave travels 10 meters. We don't know whether it's 10 meters to the left or 10 meters to the right. But if we can find the same type of point on one graph and the other graph that are 10 meters apart from each other, those should really be the same point. In retrospect, it looks like 7 isn't going to work very well, because 7 forward or 10 forward and 10 backward from 7 would be -3 and 17, both of which are off the graph. So let's ignore that 7 for now. But can you find a location on one graph and a location on the other graph that are 10 meters apart and the same type of point? If we take a look at 4 on which graph specifically? Or wait, no, 4 was the time. Can you identify a crest on one graph and a crest on the other graph, or a trough on one graph and a trough on the other graph, whose x values are exactly 10 meters apart? Yeah, if we take a look at the 3 here, we've got a trough at 3 meters. Do we have another trough 10 meters further on? Yeah, 13 meters. So we've got a trough passing through the 3 meter mark at time 10 seconds, and a trough passing through the 13 meter mark, which is exactly 10 meters away. That's the important thing, exactly 10 meters at the 6 second mark. So that means that trough presumably has traveled exactly 10 meters in those 4 seconds. So these 2 points represent the same trough. That trough has moved as time passes, but it has moved exactly 10 meters over the course of these 4 seconds. So now that we've identified the same trough on both graphs, we can use that to figure out which direction the wave is going. And what I usually do here, and this kind of applies whether you've got 2 x graphs or 2 t graphs, the same process still applies. Once you've identified the same trough or the same crest on both graphs, if you draw out a picture of the wave, let's say we just treat this as an x-axis. The important X values we're looking at are 3 and 13. So let's say we're looking at the 3-meter location and the 13-meter location. If you think of that as like, let's say you've got somebody stationed at the 3-meter mark watching the medium, and somebody else stationed at the 13-meter mark also watching the medium. The person at the 3-meter mark sees a trough pass by at what time? We've got a trough passing by the 3-meter mark at what time?
10 seconds.
Yeah. Trough passes by the 3-meter mark at 10 seconds, and that same trough passes by the 13-meter mark at what time?
At 6 seconds.
Yeah, trough at time 6 seconds. And it's the same trough. Which one of those events happens first?
The 6th one happened first.
Yeah, 6 seconds is an earlier time. So we know that the trough hits the 13-meter mark earlier, and then later the same trough hits the 3-meter mark. So as time passes, which one of these, which direction is the wave traveling?
Should be the wave traveling to the left.
Yeah. From the earlier instant to the later instant, we're going from x equals 13 towards x equals 3. So that's traveling to the left. That is in the negative x direction. So that's how we can figure out the direction of travel. Even if we've got 2 x graphs, or if this had been 2 y graphs, or 2 time graphs, I mean, we could use the same sort of approach. If it was 2 time graphs, we'd know the difference in position. We'd use the speed to find the difference in time and look for 2 crests or 2 troughs that are that much time apart. But once you've identified 2 troughs or 2 crests or whatever that are the same on both graphs, then you can proceed the same way. Set up an x-axis, draw out the 2 locations you care about, figure out which one hits earlier, which one hits later, and then draw the arrow of time passing. Any questions on that so far? And if it's moving to the, oh, sorry, go ahead.
Yeah, I just have a quick question. So, like, you have to be given the speed to figure this out, or?
Yeah, or some other information. Like maybe instead it tells you, maybe it just tells you outright, these 2 troughs are the same trough. But the important thing is you've got to have that one extra piece of information. If all you have is the 2 graphs, that's not enough information. But if you also know the speed or 2 points that are already identified as being the same point, then you can proceed from there.
What do you mean, the same point?
Like maybe instead of the problem telling you the wave speed, maybe the problem tells you the trough at 13 on this graph and the trough at 3 on this graph are really the same trough.
And then I guess we can continue with this problem if we're still doing problem, but like, could you do that after when you have like 2 of the same at the same point or the same point?
Well, we just proceed exactly the same way we just did. We would just be able to skip all of the speed stuff. If it had told us from the beginning that the trough at 13 and the crest at 3 are the same trough, then we could just skip directly to this diagram and say that the trough hits 13 at time 6 seconds and the same trough hits location 3 at time 10 seconds. So the same as the last steps in the process, we would just be skipping the speed stuff because we would already know the points at the same trough.
But if it's the same trough, wouldn't it happen at the same time?
Well, it's the same trough in motion. So the trough is moving. It hits a certain location at a certain time, and then it hits a different location at a later time.
Okay.
So it's got different x values because time is passing, and it's a point in motion.
Okay. Okay, thank you.
Mm-hmm. And since we know it's traveling to the left, should we use plus or minus in the actual equation?
the plus.
plus. And then it looks like the only parameter left is phi, and of course the amplitude, but that's not really shown on the y-axis here, so I would ignore that, just leave it as a. But for the phase shift, how would you find the phase shift at this point?
Would it be the same way that we use a couple?
Yeah.
So
Yeah, you can use the
yeah,
exact
we
same
just
method.
just choose the random trough or crest, and then for the crest it's gonna be pi over 2 for the phase difference, and for the trough it's gonna be 3 pi over 2, and then just solve for the
Mhm.
mm,
The phase shift, yeah. Yeah, exactly. You can choose any crest or trough as long as you can clearly see the coordinates for it. Like for instance, you could choose this crest and say for this crest, x is 10 and t is 6. Write out the total phase, that is the stuff inside the sine function. Fill in that x value, that t value. And since this is a crest, we'd set the total phase equal to pi over 2 and then solve for phi. Or if we'd use the trough, set it equal to 3 pi over 2 and solve for phi. Any other questions on that?
Casey, I don't know if you had the chance to actually look at the activity 8.7, but in class, we didn't do, we did something that is so my TA, what he did was he took the delta x and he divided by the wavelength to know where is that wavelength on the graph. I feel like it's
Yeah, there
kind of
are
different.
several different ways to do this. I think what that approach is looking at is converting the difference in x into a number of cycles.
Oh yeah. He was talking about like what is that cycle? So, but for this question, because like your way is clearer, it makes more sense to me. So I can
Mhm.
apply your way to all kind of different
Yeah, this method should
question that
work
is like
if you got
similar
two
to
x
this.
graphs or two time graphs, as long as you also have information about the speed or a point in the same trough or the same crest on both graphs.
Okay, and then I was wondering about if the speed is changing, like the direction of the wave can also change.
Yeah, like if we had been given a different speed, but the same graphs, then we would get a different value for delta x. So we'd have to choose perhaps different locations. Like for instance, let's say we had a speed that we solved for delta x and we found that delta x was 2 meters instead of 10 meters. If we look for locations that are 2 meters apart, we might have, for instance, 4 and 6. If 4 and 6 were the same crest, then that means it hits 4 earlier, it hits 6 later. So that would mean it's going to the right.
Gotcha.
So if we had been given a different value for speed, we would get a different value for delta x, and that might lead to the opposite direction of travel.
Alright.
But it depends on how the numbers work out.
Okay. Thank you, Casey.
Mhm.
And
Any
then
other questions on that one?
for the same activity, they ask you to graph the y versus t graph
Mhm.
when t equal to 0. Can you
You mean
share?
the y equals x graph, or y of
Oh,
the
y
function
equal
of
to x. Yes, y equal to x graph when
or
t
y is a
equal to
function of x?
0.
In that case, you
Mhm.
could just fill in that t value for t, and then you get y equals a function of x. So you could graph that.
Let me say that one more time. Sorry.
If you have a t value, you could just fill in that t value for t and simplify the equation, and then graph y equals that function of x.
Oh, gotcha. Okay, thank you.
Or alternatively, if you know information about that time, like let's say that time shows up on one of your graphs, you can use that graph to figure out what's the y value based on the graph, and then use that as a data point on your new graph. Like for instance, if we wanted to make a y versus, based on this information, if we wanted to make a y versus t graph at, let's say, x equals 7, What's the one piece of information we know about x equals 7?
It's a trough
Yeah, we know that x equals 7 is at a trough, specifically at what time?
at 6 seconds.
Right. So that means our new y versus t graph will have a trough at time equals 6 seconds. So you could draw out your y versus t graph, and at 6 seconds, you know you've got a trough. We also know the period is 2.4 seconds. So from 6 seconds, you could go 2.4 into the future, that's another trough. Or 2.4 into the past, that's another trough. So you can at least mark where all the troughs will be. Then halfway between two troughs, you got a crest, and then you could draw in the rest of the graph from there.
Gotcha.
So
Thank
if
you.
it's at least at an x value that you have on this graph already, then you can get information from the graph and sketch the new graph without needing to really do many calculations. Just you need some anchor point, and you need to know how far one cycle is. Any other questions on that so far?
I think this might relate to this question. So is it always that you'll have pi over 2 is always going to be a crest, and then 3 pi over 2 is always going to be a trough?
Yes, but you can also always add or subtract whole number multiples of 2 pi to those. So for example, crest could be pi over 2, or if you go 2 pi further from that, pi over 2 plus another 2 pi would be 5 pi over 2. Or if you go another 2 pi beyond that, you get 9 pi over 2. Or another 2 pi beyond that, you get 13 pi over 2. And you can also go backwards. If you subtract 2 pi, you get negative 3 pi over 2. Or subtract 2 pi again, you get negative 7 pi over 2, and so on. So all of these as values of the total phase would be crests. Because if you add or subtract 2 pi to an angle, you're not really changing it.
Gotcha. Would 3 pi over 2, would that be like a trough or a crest?
Well, if you take the sine of 3 pi over 2, you get negative 1. So that's going to be a trough. But again,
Okay.
also you could you don't have to say every single trough is 3 pi over 2. Any trough on its own can be treated as sine of 3 pi over 2. But you could also add or subtract any whole number multiple of 2 pi to that, and it will still be a trough. Because 2 pi is one full cycle, so no change. In fact, if you,
gotcha.
for any single trough or any single crest could be treated as pi over 2 for simplicity. But if you treat one specific crest as pi over 2, then the next crest will be 5 pi over 2, and the next crest after that will be 9 pi over 2, and so on. Or in the other direction, negative 3 pi over 2, negative 7 pi over 2, and so on. So each of these values can represent a different crest. It's just that if you're looking at any one crest in isolation, you can just treat it as any one of these, and pi over 2 is usually the easiest.
Thank you.
Mm-hmm. Any other questions on these graphs? All right, then let's take a look at a Doppler effect example. Let's say we have two objects in motion. Let's say we've got, let's say, two cars. So we've got your car and another car. And let's say you're driving along at a known speed. Let's say you know that your speed is, let's say 20 meters per second. and the other car is also driving, let's say, away from you at maybe 25 meters per second. And let's say the other car is emitting a sound. And you hear the sound at a frequency of, let's say, 500 hertz. So you're in your car and you're listening to the sound made by the other car, and you hear a sound of 500 hertz. Is that the sound the other car is actually producing?
No,
What's changing it? Why would you be hearing a different sound than what the car is actually making?
because of the velocity and because the direction that that your car and another car are moving.
Yeah, the fact that you as the listener are moving and the other car as the source of the sound is also moving, that's going to introduce a Doppler effect, which changes the sound you hear. The sound you hear, 500 hertz, is not the same as the sound that was created by the car in the first place. So let's see if we can figure out what sound it was actually producing in the first place. So that's the big question here. In this case, the question is, what frequency was the other car actually producing? And I think we have enough information here to find that out. To start with, what's the usual equation for the Doppler effect that links the frequency you hear to the frequency that was being produced? How's that, or what equation have you been dealing with for that?
So it's the frequency of the observer.
Frequency of the observer equals what?
So velocity of the air, speed of the air,
Sorry, I couldn't hear that.
speed of the air. That 350 something.
Yeah, it's going to be a ratio of speeds.
Yeah.
I usually think of it as frequency of the source multiplied by this ratio as a modifying factor. And what is the usual way that ratio is written?
Is it, oh, go ahead.
Oh no, you go ahead. Sorry.
Oh, okay. So numerator is just, I think it's velocity of sound, and at the
Mhm.
bottom it's velocity of sound plus or minus velocity of source.
Yeah, and we're also going to have plus or minus velocity of the observer here as well. They're both going to make a difference here because both the observer's speed and the source's speed are going to make a difference, are going to play a role here. Because if the source is moving, then that causes the sound waves to get more stretched out or more packed together, depending on the direction of motion. And if the observer is moving, like let's say you're running towards the source, that means you're going to be encountering more wavefronts per second. Any questions on that equation so far? And yeah, the V here without a subscript just represents speed of whatever wave we're talking about. In this case, sound, but the same equation applies to other waves as well. It's just sound is usually what we talk about, what we use it for. But in general, the frequency that's heard by the observer, the observed frequency, is going to be the frequency created by the source modified by this ratio of speed differences. And what determines whether we should use plus or minus in these?
So on the numerator, it depends on the observer, whether the observer is moving away or closer to the source.
Yeah, and same thing with the numerator, just talking about the direction the source is traveling. So both of those plus or minuses are about the direction of travel from the observer and from the source, right? Whether they're moving towards or further away. So let's see if we can fill in some values here. We know some of these values. For instance, what's speed of the observer here?
20.
Yeah, the observer, that is you in your car, are moving at 20 meters per second. And what about the 25 here? What would that represent?
Velocity of the source.
Yeah, the speed of the source is 25 meters per second. And should 500 hertz be frequency of the source or frequency of the observer?
It's the observer.
Right. 500 hertz is the frequency you hear, not the frequency being produced. So frequency heard by the observer will be 500 hertz. And frequency of the source is unknown. That's really what we're trying to figure out. What frequency was the other car actually producing? That's the unknown frequency of the source. And what about speed? Do we know the speed that sound travels in air?
350.
Yeah, that's about 350 inch meters per second. Or I guess it ranges between about 340 and 350, depending on conditions like, I think, largely the temperature and humidity of the air. But let's say we're assuming 350 for now. Typically, I would expect that to be provided, but generally, sound in air is around 340 to 350 meters per second. So it looks like all that we still need to figure out, other than a bit of algebra, is should we use plus or minus here? And I would take a look at each one of those individually. For the numerator, you're moving towards the source. If you're moving towards the source, would you expect that to cause you to hear a higher or lower frequency than what's actually being produced?
Higher.
Yeah, because the source is producing sound waves. Let's say this sound wave, this sound wave, this sound wave. If these are just the crests as they're spreading out. If you were standing still, you would be hit by a certain number of those crests per second. But if you're moving towards the crests, then you're intercepting each crest sooner than you otherwise would. So you're experiencing more crests per second, and more crests per second literally is the meaning of higher frequency. So we should expect your motion to lead to the result being larger. And for the numerator, would plus or minus lead to a higher result?
Plus.
Yeah, so we want to use plus there to get a larger result. As for the denominator, the other car is moving away from you. If the other car is moving away from you, what does that tell you about the waves behind the car? That is, the waves traveling in your direction. Are they going to get more spread out or more close together?
More spread out.
Yeah, the waves traveling backwards behind the car are getting more spread out, as opposed to the waves in front of the car are going to get packed closer together. So the waves in front of the car get packed closer together, the waves behind the car get more spread out. And yeah, more spread out is going to mean a lower frequency. You can see this from the speed equation that speed equals wavelength times frequency. So a larger wavelength further apart means a smaller frequency. You can also look at it as if the waves are spread further apart, then there's going to be fewer of them hitting your location per second. So we should expect the other car traveling away from you to result in a lower frequency. Again, looking at just the other car's motion in isolation, assuming for the moment that you're standing still. So we should expect this effect to create a lower frequency. And to get a lower result, what do we want the denominator to become, larger or smaller?
Larger.
Right, so we should be using plus or minus here. Yeah, that'll be plus as well. And I generally find it useful to think through these things in these terms. For each individual effect, your motion, like the observer's motion and the source's motion, ask yourself for each one of those individually, should you expect that to cause a larger result or a smaller result? And then choose plus versus minus accordingly. Any questions on that setup so far?
Yeah, I have a quick question.
Mhm.
Can you go over again the denominator and how you got that it would be a lower frequency?
Yeah, if the other car is moving away from you, in general, if a source of a sound is moving, then the wavefronts in the direction of motion get bunched up closer together, versus the wavefronts in the behind direction get more spread out. And you can kind of see this if you take a look at the motion itself. Like, let's say you've got this moving object. Let's say it's moving to the right. Let's say at this instant, it emits a crest. That crest is going to spread out. As time passes, the crest spreads out in all directions, still centered at the location where it was created. But as time passes, the source is also moving to the right. So the wavefront is centered on the location where it was emitted from, but the source has moved on since then. The source now emits another crest. Let's say this is exactly one period later. If the source emits another crest at this time, and then let's say we allow a little more time to pass. So the original wavefront spreads out further. The new wavefront that was just emitted also spreads out. Centered at the location it was emitted from. And the source continues to move. And let's say at this time, let's say this is one period later, the source emits another crest, another wavefront. And this pattern continues. What do you notice about the spacing of the waves in front in the direction of motion?
They're shorter and they're like together more.
Right, they're bunched together much more closely, a much shorter wavelength. So in the direction of motion, we have a shorter wavelength.
So with the denominator, so Vs is supposed to be the velocity, or to determine plus or minus, the plus is that you're going to want, is going to be, I think I'm getting confused with the top and the bottom, plus or minus. They're both different, right?
Yes. That the,
So like,
sorry, go ahead.
so like the denominator, if you are adding in the denominator, you're saying that the objects are moving away from each other? Or is it just like one object?
Well,
Are you supposed to look at it like one of the objects are stationary and the other one is moving away?
well, in this
Even
case,
if they're both like moving?
they are both moving, but yeah, I would look at it one at a time. Like if we're looking at just the denominator and trying to decide should this be plus or minus, I would focus on just the motion of the source and assume the observer is staying still for the moment. If you imagine the observer is staying still and just the source is moving away from the observer, in the behind direction, the waves are more spread out. That's a larger wavelength, which would mean a smaller frequency. That is, in the direction behind, the direction opposite to the direction of travel, the waves get more spaced out, further apart. So that's a longer wavelength, and that suggests a smaller frequency.
Got it. Okay. Okay. That makes sense. Thank you.
And since it's the denominator, to get a smaller result, we want the denominator to be larger. So we would use plus here. Any other questions on that so far? And by the way, this applies to other waves as well. Any wave, not just sound, that's being emitted by a moving source. And I think this is perhaps most visibly obvious in ripples on a pond. If you just got like a buoy bobbing up and down, it's going to create ripples spreading out as concentric circles. But if you've got a boat that's moving slowly, the ripples are going to look like these circles that are more spread out. Each one of them is still a circle as it spreads out, but the circles are no longer concentric. They're centered at locations that are moving further and further along. But going back to the equation here, if we simplify this a bit, we get 500 hertz equals frequency of the source times 370 over 375. And what happens to the units there? If we've got meters per second in the numerator and meters per second in the denominator? Yeah, those cancel out. So that means the result, 370 over 375, is a unitless ratio. And this usually happens if you've got a fraction of the same type of measurement, speed over speed, or distance over distance, or time over time. As long as the numerator and denominator are the same units, then the result is a unitless ratio, which is good because we want the frequency to have the same units as the hertz over here. And then how do we isolate frequency at the source? What's the opposite of multiplying by 370 over 375?
Divided the 500 to that fraction.
Yeah, if we just multiply by the reciprocal, 500 hertz times 375 over 370, then that'll tell us the actual frequency. 500 times 375 over 370, so about 506.7 or 506.8. So that means the actual frequency that was originally created by the other car was 506.8 hertz, but that gets modified by the Doppler effect, so you hear a lower frequency than what was produced. That doesn't mean what you're hearing is incorrect. It's just that what you're hearing and what was produced are not the same. It's changed by the motion of the objects. So that's the core idea of the Doppler effect. If the object is, if the source of the sound is moving, or the observer is moving, or both, those are going to create changes to what is heard versus what is produced. Any other questions on the Doppler effect? Or any other quick questions before I go?
I don't know if we still have time, but
Sorry, what was that?
I don't know if we still have time, but are you okay with going over one of the quicker question of Dina this morning?
Is this the one on interference of waves, superposition?
Yes. Mm-hmm.
I
So
don't
the
think we're
one
going to have.
that-
I don't think we're going to have time
Yeah,
for that
time.
this time, but we can go over interference next time. And I've also
Okay.
got some, if you take a look at the videos linked off of math.ncheese.org/P7C, there should be links to some YouTube playlists of my previous workshop recordings. And there should be several of those that are all about interference. So take a
Alright.
look at those for some other examples, and we can work on that next time as well.
Okay. Thank you.
You're welcome. See you next time.